theory course instructor and has been giving lecture for the last few days, and he will be giving lectures for his students also for the CAN participants. And we are thankful to him that in addition to his CAN lectures, he also agreed to give us an institute lecture and tell us about his recent exciting work. Prof Tahara obtained his doctoral degree from the University of Tokyo, and then he was also there for another year as a research associate. Then in 1990, so that was in 1989, he obtained his doctoral degree. Then in 1990, he moved to Kanagawa Academy of Science and Technology as a research associate, and then he joined the Institute of Molecular Science at Opto-Science, Japan as associate professor in 1995. In fact, I was in Japan for a year last year and the year before, and many physical chemists I met, or molecular scientists I met in Japan, who said that, oh, I was at RMS at some point of time. So I think that is one institute which has groomed a large number of scientists at their early career, and then they have moved out of IMS and joined many different universities and institutes. So from IMS, Prof Tahara joined RIKEN as the chief scientist in 2001, and he has been continuing there since then. Prof Tahara has published a large number of papers, more than 150 original papers and 30 reviews, and he has served as the editorial board members of many key physical chemistry journals, such as the Journal of Physical Chemistry, Journal of Chemical Physics, and he has also been serving the editorial board of Chemical Physics. Dr. Tahara is currently the head of the Division of Advanced Laser Spectroscopy in the Spectroscopic Society of Japan. He is also in the board of the Spectroscopic Society of Japan, in the steering committee of Japan Society for Molecular Science and board of Japan Society for Molecular Science, and he is also in the advisory committee of Institute of Molecular Science. Dr. Tahara is currently the project leader of JSPS MEXT project of on invaded area soft molecular systems, which is made up of 45 project investigators across Japan. And he is also the head of the RIKEN pioneering project molecular systems research, which is made up of 15 project investigators both from inside and outside RIKEN. Dr. Tahara has received many awards. Some of them include the award of Research Foundation of Opto-Science and Technology in 1995, Morino Science Award in 2000, Outstanding Young Researcher Award in 2001, IBM Japan Science Prize in 2004, the JSPS Prize in 2006, the Chemical Society of Japan Award for creative work in 2012, the Distinguished Asian Visiting Speaker Award at the University of Alberta, Canada in 2013. He also received the Japan Society of Molecular Science Award in 2017. This is, of course, only a partial list. He has received many more awards, which I am not going through now. So, with this brief introduction, it's my pleasure now to invite Tahara to give this evening's discussion.
Thank you very much for a very detailed, kind introduction. So I'm extremely happy to visit the IIT Kanpur again, and this is a great place, and it's just great to see my old friends and new friends. In particular, I like to how to become the host of the YAN project, which is now full great place, I'm proud to say, and I was lucky to have a chance to work with you in my lab. Okay, so today I'd like to talk about the frontier of the spectroscopy, and what under the title "The Wonder World Seen with Light." And first, I'd like to start my talk by showing this slide, showing the seeing the observing. In my opinion, all the science and technology, in my opinion, start with seeing. by literature eyes. Actually, so astronomy started by seeing the stars, and also, many things start with by eyes. Actually, our human eyes is very great detector. So sensitivity is photon counting level, and we have a time dimension because we can catch motion of the materials. Then, however, recently, we feel the limitation of our eyes. Then we have to use many kinds of detector lights, which invented with the technology. And then our seeing changed to observing with such kind of advanced devices. So then, this is what we are doing. Is the spectroscopy, particularly advanced spectroscopy. So basically, it's based on the seeing. And actually, I'm chief scientist weekend, and weekend is quite interesting place. In particular, chief science system is quite peculiar. It is a design directable on now, and in weekend is big. It's the biggest and the oldest research institute in Japan, and we have only 50 chief science laboratories. We don't have any departments. We don't have any local structure for the chief scientist. So that I regularly on daily talk with the chief scientist who is doing the nuclear physics, theoretician to the biologists who are talking about epidemiology or something, IBS things. Then for the great scientists that sometimes we have to explain what we're doing to such kind of my colleague who don't know detail things, and they ask me, what are you doing? Then I have to define myself, and I have to, mention, tell them about the motto of my laboratory, which is nuclear spectroscopy. And my motto is that if we can see what we could not see before, new science will emerge. It's very simple. And this is actually what we want to do with spectroscopy. It means that what we want to do is not just using advanced spectroscopy. We want to create a new way of doing spectroscopy to see some very new fundamental phenomena in nature and start something. Okay, this is normal. So then I would like to start with this kind of things. Now there's light in spectroscopy laser. So this is great. And in particular, we are using the so-called ultrafast laser, which generates very ultrashort optical pulses. And duration of the pulse is picosecond, which is 10 to the minus 12 second. Okay, so it's 10 to the minus 12. What does it mean? It's actually 1 million second. And femto, which we will talk today, is actually 10 to the minus 15. It's 1 to 1 trillion seconds. Actually, I didn't know this in English word before. Then, still, it's difficult for you to feel, intuitively feel that short. Then I will explain by how short it is by showing 2 examples. One is, it's usually used for explaining shortness. The distance that light travels with that short period. The 1 second, light can travel 300,000 kilometers. The light goes around the Earth 7.5 times or something. But with 1 picosecond, light can travel only 300 microns. Okay. And 1 femtosecond, light can travel only 0.3 micrometer, which is 300 nanometer. It's very short. Okay, still, here's this one. Then let's think of using the time. it's quite difficult to think about the shorter time scale, but we can think about the longer time scale. So I say that the Bose relation is 10 to the minus 15th, but we can think about 10 to the 15th, which is quite long, to feel that how different 1 and 10 to the 15th. Okay, so we can feel the 1 second. 1, 2, 3. This is 1 second. Then thinking about 1,000 million. Actually, 1 million is 30 million seconds. That's quite long, but still, it's not so long. Then goes. Actually, here is 10 to the 12th. Actually, the people say, I don't know who see it. 5 million years. Some people say that 5 million years since we were separated from chimpanzee. But still, we cannot reach the 10 to the 15th. The 10 to the 15th here. And here, we have time. The times. Some people say that 16.5 million years since dinosaurs were extinguished. Okay, so actually this is when our universe was born. We are approaching that length. Actually, this is 10 to the 15th, since it's between the time of we are separated from chimpanzee and dinosaurs are distinguished. Okay, suppose that this is 1 second, this is 1 second. So you can now feel how short the femtosecond is. It's extremely short. So now we explain 1 second, but we have gigantic number of femtoseconds. Okay? Alright, so then we're talking about what we can do with such kind of short optical pulses. One is observing ultrafast phenomena using ultra-force optical pulses. So then issue is ultrafast phenomena. Actually, in molecular science and probably in general science, one of our motivation is to know, the question is, how does chemical reaction proceed? This is one of the driving forces to push science, frontier of science forward. Okay? Then let me explain the basic thing, because this is a general talk. You are talking femtosecond. Suppose we have benzophene. Actually, this work is the work with which I got PhD degree. So that I like this molecule very much. And when we irradiate light, the benzophene shows the reaction to form benzophenol. Actually, 2 benzophenol coupled to each other next to benzophenol. Okay, so then maybe in this order, we might have organic chemistry. Okay, so then in the book of organic chemistry, photochemistry, this is very typical photochemistry. It says that make the benzophenol, the amine solution, in isopropyl form and some acetic acid, right? And turn it around in order to block air. Actually. Then put some under sunlight. So here in India you have very strong sunlight, probably reaction proceeds a little faster. but actually I did it in Japan when I was a student. It took 1 day or 2 days to see the crystal of benzophenol. So it takes 2 days. Oh, come on. What is the importance of femtosecond, picosecond? The action takes place days, hours. Okay, and actually this then in Greece or Roman period, great scientists think, I would like to know how reaction proceeds. Then that guy might, we have benzene in this solution, which is transparent, and 2 days, benzene pinnacle is, is formed. Then, okay, I have gray eyes. Okay, so I decided to figure out what's going on. Okay, I sit on the next flat and see what's going on. Seriously. Okay, yeah, okay. You laugh, I laugh. Well, usually before the modern science, this question and this approach surely great. Don't you think so? Then what? But something wrong. Everyone knows that something is wrong, because what we observe is just amounts of the benzene crystal is increased. Right? We cannot see what's going on between benzophenone and benzophenone. Then the question is, what's it wrong? Actually, situation like this. This is benzophenone, and that is benzophenone. But actually, photon comes in, the one benzophenone is excited, suddenly transforms to benzophenone. This is start, this is the goal. The actual time this molecule actually keeps running on this course is very short. You understand? So that if you see from far, you can recognize the kids molecule running. So that what we can see is just from far, because we cannot see this molecule. What we can see is the number of the molecule in reactant decreases, and number of the product increases. This is actually what we see with sitting next to the flux. But what we want to know this one. Okay? Then what we have to do is we use some big sounds. All kids are surprised and excited. They start running together. Okay, so it's quite straightforward. Then all kids are here. Then we can see the molecule on keys running. Okay? Then, in order to make this observation easier, it's quite weird if you did in the real world make the room dark and you make fresh. Okay, then dark. Then let's take a photograph with flash. Then by changing timing, we can take a picture running here, here, here. Do you understand this principle? Actually, this is a principle of flash photolysis for Pantro, and this idea got Nobel Prize in 1967. Okay, again, Norwich Porter got Nobel Prize. And this idea is simple, but it's quite important. And even though we use picosecond, femto, anything, we still work on this principle. That's why you deserve Nobel Prize. Right? So I learned from textbook in first experiment that's done in that way, reaction tube, and they makes real flash. Okay? Then from here they take a photograph, which means measure the color by measuring absorption spectrum. Okay, so then this is this is a fundamental spectroscopy. You irradiate the white light. It contains many color. Then some part is absorbed by sample. Then we can see which part is absorbed, which corresponds to color. Okay, so concerning this reaction from benzophenone to benzophenone, 1 picosecond, we have first excited state, which is called S1. It shows the this kind of absorption. So if you can see by eye, initially the sample is transparent. but it becomes a little dark and 2 pieces coming. Then that gives a very sharp peak. Then probably the color changes to the purple. Then this categorized form, it shows different absorption. Then color becomes red. Then finally, with the benzene apple with crystal again is transparent. So actually, by using such kind of laser and flash photoresist, in fact, this experiment is just seeing the color of the sample. Okay, then this kind of experiment, with reaction knowledge, now we know that reaction is not like the peak elements case of molecule run the flat, racetrack. It has some bump and peak and bump and peak and something like that, which we call potential in surface. And here we have reaction internet. We have temporary population there, and this points which called transition state. So then we have such kind of concept. She has what is smiling, and this is the concept of potential in surface. Okay? Okay, then let me talk about femtosecond. 1/12 second. So time scale of this one, actually this spectroscopy got again Nobel Prize, 1999. Maybe you know that name, the Professor Ahmed Zubel. Unfortunately, he passed away a while ago. And because of the femtosecond spectroscopy, he named it femtochemistry. So he got the Nobel Prize alone, but in my opinion, everybody said that maybe because we have many great scientists in this list. I would like to mention Professor Shank, Professor Ostrasa, and Graham. And we think that maybe 3 can share. But unfortunately, Nobel Prize can be given only 3. The committee cannot choose a 3. Then he got Nobel Prize alone. But anyway, this is great thing. Then the issue of the femtosecond, why femtosecond time scale is important, different from picosecond. It means the femtosecond is time scale of vibration of nuclear motion. Okay, so motion or change of motion vibration of the nuclei is a kind of the most important thing in chemistry, because chemical reaction is rearrangement of the nuclei. Okay, so then observing the motion of the nuclei is quite important for chemistry. That's why I suppose I'm not a member of the selecting committee. But if we try to rationalize why chemistry and Nobel Prize is that the femtosecond time region is the time scale of the nuclear motion of the molecule. In fact, we can directly measure vibration of the molecule by using femtosecond spectroscopy. This is simple carbon tetrachloride. We have carbon here. It has 4 chloride. Okay, so if we excite this liquid with femtosecond, then molecule starts coherent motion, which is called vibration. That vibration is observed like this kind of beating picture. Actually, observing this beating picture corresponds to the observation of classical motion of the molecule. Okay, so certainly this is picosecond, this is femtosecond, so that the beating or molecular vibration occurs in the time scale of femtosecond. Right. Okay? Then actually, this is one of the first projects I did after I started my lab. So this is a setup. You can see this guy is me. Please don't laugh. Believe me, this is me. At the age of 34, 35. And he is Dr. Matsuo. And he's my first postdoc. He's now full professor in university. Okay, So observing this kind of nuclear motion is great. Then next we try to observing nuclear motion, because this is just a simple liquid. Just a simple liquid. But next target for me is observing nuclear motion of reacting molecule. I would like to see the vibration motion of the molecule which is reacting. Okay? Then I chose this reaction, cis-strain isomerization from cis to trans. It is known that that isomerization occurs with 1 picosecond. I try to observe nuclear motion during this fast reaction. Alright? Then we did the experiment. We excite the molecule and the cis-strain start isomerizing. And we introduce second short pulse to initiate vibration of the molecule in the excited states, which is reacting. And actually this leading feature is a nuclear motion of the reacting excited state system. Right. Then with the, combined with knowledge from this kind of measurements with advanced quantum chemical calculation, actually our collaborator is Taketsubu. And we had this picture of what's happening after excitation. And then we just observed the initial part of the twisting. And this CCW twisting. But you can imagine the cis-trans isolation occurs like this. But in fact, cis-strain is already distorted in the ground state. So that what happens? So that this pairing doesn't move substantially. Only central CC double twist, at least initial stage. Right? And we did this experiment. Okay. So there you can see how it is distorted. Alright? Can you hear me? Alright, and actually I did this work in about 10 years back. And luckily, because this was conceptually new at the time, and the science likes that work, and the paper was published in Science, I was very happy. Then, I didn't regularly read Science, but my colleagues, my friends said, "Oh, Tahei, in the same issue, Science published a perspective. If Science likes some article, they prepare some perspective. They ask somebody to write, explanation about the work." And this Professor Brown kindly wrote about this perspective work. It was quite interesting. If somebody explained nicely about our work. Oh, it's great. But in this perspective at the end, Professor Brown wrote, although the method presented is technically demanding, sure, I knew technically demanding, agreed, and then it could be applied to a wide variety of photoinitiated reactions, including those that take place in complex and environments such as proteins. Actually, I was exhausted when I did work. Okay, this was difficult. And come on, David. I met him later. Come on, David. What? I'm talking. What are you talking about? Do you want me to try protein? At the time. But actually, after 10 years, now we can apply this method to protein. Point is, in order to measure the change of the motion of the complex system, we have to observe all kinds of vibration up to high frequency side. So in order to observe the high frequency vibration, we need short pulse because we have to time resolve the high frequency vibration in time. Okay, and also we need high signal isolation, so we have to prepare very ultra stable, very short optical pulse. Okay, then this is set up now. Then by using many techniques, finally we got the pulse about 6 femtoseconds. Then we measure several proteins. I'd like to show one example with photoactive yellow protein. And photoactive yellow protein is blue light photoreceptor of some bacteria. And people believe that it triggered it's responsible for negative phototactic response. So phototactic response means that blue light is quite harmful. So if we irradiate blue light on the bacteria wants to escape from the light, which is negative phototactic response. And this is a protein which triggers that response. The initial event is we have paraquamatic acid as chromophore in this protein. Again, cis-trans isomerization occurs after photoabsorption, which triggers this response. Okay. Then we apply this method, and actually this is a nuclear motion chromophore in protein. And nicely we observe the specific feature. By changing the delay time, we can track what's going on. So now we nicely apply this method to complex system like protein. Then with that kind of the measurements, we came to know the cis-trans isolation occurs, but first ground state intermediate is heavily twisted, not flat cis. Such kind of trapping of the heavily twisted product cannot be seen in solution. Probably it's due to the effect of protein matrix. Okay? Alright. So first I talk about how to use the ultrashort pulse nicely. The one of the way to use is take advantage of short temporal duration with ultrafast spectroscopy. The second one is short pulse has very high peak power, very high. The reason is, think about 1 watt light. 1 watt is quite dark. Okay? Even though we have light of 1 watt, maybe it's too dark to see, to read the book under the light. But ultra-short pulse means that that energy is concentrated in very short time. You understand? So it's dark. Suddenly energy is concentrated in short time. So then peak in short time power can be very high. And we have Morino laser which delivers 100 femtosecond pulse at repetition at 100 megahertz. We consider this is weak femtosecond laser. But if we calculate the peak power, the peak can be 10 to the 6 watt, which is 1 million watt. So then still average power 1 watt, but by using techniques of regenerative amplification, we can store the energy, and by reducing the repetition rate, we can concentrate more energy on 1 pulse. Then the repetition rate decreased from 100 MHz to 1 kHz, but peak powers increase up to 10 to the 10th. It's 10 billion watt. So 10 billion watt light, if it's CW, I'm pretty sure that we all evaporated. But this because it's short, more can survive. But still, it shows quite actually technique of the generating this kind of short pulse got Nobel Prize this year, and these two, Professor Moore and Strickland, got Nobel Prize because of this techniques of shaft amplification. Okay, so then because it's quite high, the molecule survive, but rest of the molecule start behaving in a weird way. Okay, so then when light is weak, we have polarization. This is the essence of the spectroscopy or response toward the light. When light is weak, molecules consist of the nuclei, which is positive, and electron, negative, right? So it's basically neutral. But if irradiate light, light is basically electromagnetic field. Forget about magnetic field. Just think about electric field. If we apply electric field, negative electron is slightly dislocated in this direction, but positive nuclei are slightly dislocated the other direction. Then we have some polarization. Understand? So then, when light is weak, this polarization should be proportional to the electric field, which is linear response. Then it means that when we irradiate this frequency, polarization has same frequency, right? So then it means that we irradiate blue light, the molecule can absorb blue light or emit bright, reflect blue light. So it is a spectroscopy we know. But come on, we have such kind of huge power. Then suppose that this is a kind of the spring. When the force is weak, we know flux do. You understand? It's linear. But if you try to, lengthen the, spring brutally, then spring cannot respond in linear way. Suddenly it becomes longer, or suddenly spring resists to be lengthened. So response becomes deviated from linear. Then response should be written by in Taylor expansion. Then lowest term is the second order. If you think about second order, electric field is basically cosine. Then response is cosine times cosine. Then a formula of the cosine. Then we have component which has frequency of sum of the incident light and difference frequency. So that it means that polarization, frequency of polarization can be different from the frequency of the incident light. So it means it emits different color from the color of incident light. This is nonlinear optics. Then actually nonlinear optics can, developments on nonlinear optics won the Nobel Prize in 1981. Professor Bromberg is a key person in nonlinear optics. Alright, then by using this nonlinear spectroscopy, we can study interface phenomena. Okay, so interface is very important. A liquid interface and interface is very important. For example, so you have battery, then the battery, the interface is important. And environmental chemistry, the major part is the chemistry occur in the surface of the aerosol. It's a interface. But we don't know much about what's going on at the interface except for metal interface under the high vacuum. Right? The reason is, suppose we have a liquid interface, for example, air cooler. What we want to know is the property of this molecular interface. But in fact, we have the same molecule in the bulk. So if we use ordinary spectroscopy, the signal from the bulk dominate the signal, so we cannot get the information about the interface selectively. Then we have to use some special means to selectively observe the molecular interface. Okay. Actually, luckily, minor principle of the physics. Some the region where the inversion symmetry is broken. It sounds quite complicated. It means that inversion symmetry is that if we make the world upside down, all the three dimension, if the physics doesn't change, the system has inversion symmetry. In fact, we don't have inversion symmetry. I'm not inversion symmetry, but sometimes locally we have some region where we can practically take the inversion symmetry. Actually, water, bulk, so taking this one, then making the inversion. You cannot distinguish the difference. In the sense of bulk, you can have the inversion symmetry, but interface doesn't have inversion symmetry. If we change the z-axis, water goes to the up, air goes down, so that it's not equivalent from before the operation. Then interface doesn't have inversion symmetry, so it means that this kind of spectroscopy can selectively monitor the molecule at the interface because inversion symmetry is broken at the interface. Okay? So then think about water. You have a cup, glasses, which you fill with water. So in the bulb, okay, so we have, stop. But we have, okay. I should stop. But anyway, in the bulb, water has a lot of different hydrogen bonds. It's very complicated. Then, because of this complexity, if you measure the OH stretching frequency, OH has a variety of different hydrogen bonding. So that OH, this is kind of IR spectroscopy spectrum, showing the strength of the OH bonding. Because the hydrogen bond has a very dry intensity that is broad. Okay? Then, Professor Morino in Berkeley measured this water by using so-called sun-fluctuation spectroscopy. So in which he applied infrared pulse and visible pulse and observed the the generation of sun frequency. By changing infrared frequency like this, if it becomes vibrational resonance, it gives the vibrational spectrum. So that in that way we can measure the vibrational spectrum of the water at the interface selectively. Then what they report interface spectrum like this. Okay, so here we have blue bands like a bulb, but here we have very sharp bands which we cannot see in the spectrum in bulk. Still, I remember that this paper, was published because at the time I got just PhD degree, and then everyone sharp. Certainly, the spectrum itself shows that it's interface. The reason is, at interface, certainly we have hydrogen bonded water, OH, which corresponds to, which gives rise to these problems. But at interface, because one side is air, we can have the OH which stick out to the air. Okay? That OH doesn't have hydrogen bonding, so it behaves like a gas phase OH. Okay? Then actually, this free band, sharp band, is due to the free OH. So appearance of this free OH band is surely demonstrate that this spectroscopy can selectively monitor the interface order. Okay? It's the beauty of this nonlinear spectroscopy. Then, this is old, it's published early 90s. Then let me talk about what is the frontier of this spectroscopy. In this measurement, we observe the new light generated on the surface by detector. Okay? So we observe, measure just the intensity of light. But basically, light is electromagnetic field, which is wave. Okay, but measuring intensity, if we measure just intensity, information of the phase is lost. So that we miss the property of the wave of light. Then who cares? But it's important. The reason is, suppose we have this kind of move to this, okay? Then we have this kind of wave. And if the absolute orientation interface molecule shows flip down, flip up, the phase also should change by a factor of pi. But by just measuring intensity, we cannot distinguish a difference. So what is important is measuring the phase of the signal generated interface. Then by using some technique, so-called heterodyne, which is kind of phase control measurement femto compounds, we realize the measurements of phase of the signal generated interface. Then with that method, this is the OH stretching is also the interface water spectrum, which I showed, but this is a spectrum measured with new method. And it appears with sign reflect the phase. Okay, now free OH appear with positive sign, because free OH is oriented HR. But hydrogen bonded OH, this is intensity, but phase is opposite, which means this OH has H down orientation. The reason is, what we observe this OH and that OH, certainly we stick to the bulk order. And see, there are some discrepancy, but actually this spectrum is just established a few years back. All right, then I will show you one example, which is the interface water at the biological membrane. So biologists is very much interested in water at cell membrane. The property, whether it's the property same as ordinary water, was different. Then still it's difficult to apply a method to direct to the cell. Then we make the model system, model biological membrane, so which makes monolayer of the lipid on the water surface. Then we measure the water here. Right? Then first we make a monolayer with lipid tab, which is lipid, which have positive peak. And in this case, this is OH stretch band, which appears negative. It means that water, interface water, have orientation of it down. It's quite reasonable because this is positive. So water, hydrogen, has slightly positive nature, and oxygen has slightly negative feature, so that water is happy to make slightly positive edge, to be far from the surface positive. Okay, then you might doubt. Then I show the data taken from the negative head group things. Then now OH band appears positive. So it means that in this case, water is happy to orient hydrogen up toward negative charge at interface. So such kind of thing happens, which is it's quite intuitive, but this observation is possible only with this new spectroscopy. And actually, we developed this method around 2008 and 2009 at Weekend. And now this method has been spread over the world and in many groups. use this method. In India, one group actually who was Alan Mondal, who was first of mine, started this spectroscopy, and then he published beautifully recently. Okay, so in the last 5 minutes, let me talk about the real frontier of this spectroscopy. Actually, the spectrum I showed is steady-state spectrum. So it means our view about the interface water is like this. Stop. Here we have free OH, and this is a result of mode MD situation. We have free OH, and this is hydrogen bonded OH. And what we observe this molecule. But in fact, it's not static. The water interface, violently move and rapidly move, hydrogen bond changes quickly. And in this simulation, 1 second is 7 to 72 femtoseconds. It's very, very fast. Okay. So understanding such kind of the dynamics, hydrogen bond dynamics, is one of the key, because water is very important for us. There has been a lot of work for the bulk, mainly using so-called 2D IR, but nobody, cannot study the dynamics of the water at the interface. But with this method, we can do it. And then, idea is like this. We have OH, an interface. We excite that OH by certain femtosecond ion pulse, picked up by exciting specific vibration frequency. Okay? Then we'll follow up how frequency change in with femtosecond time resolution. Then we can follow how hydrogen bond change in real time. Do you understand this principle? Okay, so actually the result can be summarized in this kind of two-dimensional map. In this axis, we show the frequency at which we first excite. This is the frequency we observe after a certain time. Well, this data is the data taken immediately after photoexcitation, so that OH stretching frequency should be remembered by water within time resolution. So now you can see this relationship is tilted. Tilted means when you excite here, the observed frequency is here. We excite here, observation is here, so that OH stretching vibration or OH bonding, remember where initial frequency. Okay? Then with this kind of motion, frequency changes and map changes like this. Initially, the OH stretching, OH bond, remember its initial frequency. But memory is born, and after 400 femtoseconds, OH bond forget where it was.
So these are your calculations or
this is experimentation. Yeah, with our method. Yeah, this is our data. This is not calculation. This is real data. Right? So in that way, we are now able to follow hydrogen bond dynamics at the interface with this new method. And he asked it, we are now trying to compare with theoretical verification to figure out how interface is different from bulk. So that kind of question can be answered only with development of new method, which allow us to see what we could not see before. Okay, So today it's time's up. So that by taking advantage of the ultrashort pulse, by utilizing the short temporization, we can study ultrafast phenomena, mainly chemical reaction. By taking advantage of high peak power, we can study interface phenomena. Today, I talk about very fundamental thing, but still, observation is new. So, I would like to say that our world is full of the wonder, and still we have lots of unanswered questions, unseen phenomena, and by seeing what we could not see before, we can learn more about nature, and we can develop something which make our life better. Thank you for your attention.
Thank you, Prof Tahara. I'm sure there will be many questions from the audience. Please.
Yeah, you ended the talk by saying that you have the ultra-short pulses to study reactions, then you have high peak power to look at interface. When are you going to combine them?
Yeah, this is one. Yeah.
When are you going to combine them?
So the last one is to combine.
To study the reactions at the interface.
Yeah, this is actually what we are done doing. It's a secret.
Any other questions or comments from anybody?
Yeah.
Really nice talk. And just the last plots of your relaxation of, can you please go back to the previous? Yes. So I'm trying to understand this time is the delay that you have?
This is delay.
The delay.
So this is delay, the excitation and observation.
Right, and so this, because you are also kind of exciting with the frequencies of 3100.
Yeah.
So how are you sure that it's the interface? At the interface, because it could be also just the bulk of, because
we use some frequency generation, so that we selectively observe the only molecular
which could be also then pointing towards the interface, right? From the interface towards the bulk, because 3100 is not the free OH.
In this case, the sample is a charged monolayer, so that the surface is covered monolayer.
Okay.
So that's why. So now, actually, we are also trying to measure, apply this method to the free air-water interface.
So what is the Z-axis of this? Is the probability, or what is the Z-axis of?
Which axis?
Z-axis?
Z-axis? Yeah. We don't have Z-axis. If you want the Z-axis,
so what is the color code?
You can start the different times, spectrum.
So the color is intensity.
It's okay.
Thank you.
I can see many faces of students. I hope that I could make myself clear.
I have some questions, but I will.
Okay.
Any other questions from the audience? Okay. If not, yeah.
Yeah. Thank you very much. So
maybe I just start from this one. Yeah. So these are your heterodyne experiments. Yes. HOD in
this is
water.
yes.
Okay. So how is the interfacial time scale different from your bulk time scale? Like study air in bulk water is about 1.7.
So now we are trying to compare. The one difficulty is it's a kind of professional job. So we need to use HOD to decouple the vibration coupling. They actually, because of the sensitivity of the VSA, which is lower than infrared, so we use a little bit higher HOD concentration. So that we don't have the corresponding to the ion data. So then we are now trying to work with my friends to measure the 2D ion or something at the same same the us to have fair comparison.
Another one, if you go to your slide where you showed this OH peak for water, near phosphate groups.
You're talking about steady state?
Steady state.
Yeah.
Spectra. You showed a really broad peak, right? The interfacial OH. Yeah. I think we just passed. You had this monolayer of liquid molecules. No. The liquid molecules with the phosphate group. Yeah, it's what the end actually.
This one.
This is the next one. This one, right?
Yeah.
Okay. So the peak is very broad, right? So can you say anything about the orientation of this water interface? Or rather, which OH modes are hydrogen bonded to the phosphate group? Which are to the water? It's so broad peak, right?
For this one, it's quite, listen to you. More influence. This is phosphate. So phosphate can heavily orient the water, which has a variety of reasons. And recently, we also did the experiment on the PC. PCs, it has the phosphate and chlorine simultaneously. Then we have two components. One is the water, hydrated to the phosphate, and the other is the water and chlorine. By measuring the 2D, we can nicely distinguish them.
Thank you. Okay.
Can I ask you a question?
Yeah.
I'm not from chemical physics field, but for example, like the reaction that you had done, the benzo, like the benzo reaction that we were talking about, benzophenol, and silica and doing benzophenol. And in the reaction you are doing to understand what is to get the molecule. I'm trying to understand what is important to understand using a spectroscopy. Yes, I understand. I appreciate the technology concept, but whether it is the ring flip or just the the alpha beta double bond, like why it's so important to study that?
Okay, let me explain. In my opinion, first, if we try to pick up a very fundamental problem, first to check or to show that measurement is possible. You understand?
Yeah.
So it's very strong drivers for so-called fundamental science to push the frontier forward to increase the capability of us. Okay, so that's why we basically pick up fundamental molecule, even though that molecule would be too simple in the sense of application. Okay, then after pushing the frontier forward, we have a lot of the established method behind it. Okay, so then now they are available. Then, for use of that kind of established method, the question is important. Then, if that molecule is useful for such application, but we want to know what's going on, then we can apply that kind of the method to solve the problem.
Yeah. So
then we cannot do, of course, in ideal case, we should do both. But the fundamental, people who push the frontier forward, so just the focus on pushing the frontier forward, then people who are interested in the application, think how to develop strategy, then probably they check what is possible with our effort. Then they can use it safely to understand what's going for their system. This is the problem. This is what I think.
Yeah, so the thing is like, the studies that you had done in the fundamentally, has it been applied in the real world applications to study?
Sure. So in a sense, for interface things, now we have, we showed what we can do for air, water, or something. Now we are trying to apply to more realistic things, electro, other things, polymer, biocompatible polymer or something. Actually, what surprised me when after publishing this work, I did it thinking that pushing the frontier forward is important. But I got invitation from the society, which I have never heard, which is Society of Biocompatible, Polymer or other, which sounds more very application side. The reason is one typical example I would say. The interface was very close to the fundamental problems, very close to application. So then what they study is when we want to develop the kind of artificial organ, then rod should not be stick on the surface. Then they have to develop the biocompatible polymer. But it's an issue of the interface. But they don't know why some polymer, is okay for biocompatible, but the other doesn't. So that they want to know the mechanism. Then they want to analyze and then want to know what's going on at the interface. Then they are very much interested in our method. It's like that. So it's a kind of one of the very short-range example, but this is what I believe.
Okay, maybe one stupid question. Regarding this surface with charged modes, so people talk about this Tai Chi effect, like it can actually break the symmetry of the bulk. So for these systems, how important
it contains some. By the way, I don't like the term of Tai Chi effect. In my opinion, it is we have church. That electric field makes the orientation. Then, as a spectroscopy, it's a high-2 process for the oriented water by electric field, right? Yes, sure. So then, this contains, but these are we did experiment for steady state. We put salt. Then salt can screen the effect of electric.
So that's all. Okay. Okay, so if there are no other questions, please join me thanking before we officially conclude the session, I have present duty to perform on behalf of the it's the pleasure to present Prof Tahei on behalf of all of us.
Thank you. Thank you very much.